Hello everyone. Um, Here we are going to start new topic on backstepping control. This is basically nonlinear control design approach. In the last lecture, we had feedback linear based control, and we have studied how we can design the control for the nonlinear system. So here also we are going to consider backstepping control for the nonlinear system, and also we have MATLAB simulation. And later on in this topic, we'll have the aircraft problem, how we can apply this concept for the aircraft applications. And also we'll have the MATLAB code. So let's first start with the concept, the main concept behind this topic. And then we'll have the example and MATLAB simulation. So let me write some this concept, how we can come up for the real applications before you go to the real systems. So here, the backstepping control is a recursive control design method for the nonlinear system. So what is this main recursive method will come up, recursive control. So this kind of control you can apply for the particular structure of the system. And that is basically called recursive structure. And this system here basically, here basically you're going to have, it is primarily useful for the systems where the states can be grouped into subsystems. And this subsystem actually will have the recursive structure, subsystems. So here we'll go the step by step how we can come up the final control design for a particular system using the backstepping control. So let's first, we have the, basically this is, for example, the first case. So here, recursive system. So here, the system is divided into subsystems. And here, basically, each subsystem each subsystem depends on the previous one. So if the system in the structure, we can say the system is in the recursive structure. For example, if you have system, for example, x1 dot equal to f1 x1 plus x2, and x2 dot, if you have f2 x1 x2 plus u. So what is, so here basically u is going to be designed for x2, and this x2 going to be the control variable for x1. So for this first subsystem, we're going to have the virtual control for x2, which will help us to control x1. And that virtual variable, what will be assuming for x2, that will be used to design the overall control for x2 dynamics. So as we proceed, we will come up with the full idea how it is happening. So next part is, once you have done next part, we'll move to the next part. So here for each subsystem, a virtual control will be considered, which is as a reference signal, reference for the next subsystem. So it means, suppose for the X2, we'll consider some reference signal as a virtual control for X1, and this reference or virtual control will be used in the for the next subsystem for this system. Okay. Then we'll move to the next step. Define tracking error between actual state and virtual control. So for example, we can assume some G1 equal to X1 minus X1D. This is the error. G1 is the error. And G2, the error for the G2 dynamics, we can write G2 equal to X2 minus alpha 1. Okay, this is here alpha 1 will be virtual control. And finally, we'll come up the last step here basically. So here, Lyapunov function is constructed for each subsystems to prove stability. So these are the process we'll be following for designing the backstepping control. Now let's take an example and we'll validate this flowchart. How we can come up with the example. Here we'll be using all these steps. So example, and in this example, we'll have also MATLAB code to validate our results. So let us consider the following nonlinear system is defined by x1 dot equal to x2 plus f1 x1 and x2 dot equal to f2 x1 x2 plus u. So if you notice, this system is in recursive structure. So here, if you notice here, this f1 x1 is the only function of x1, and here, this here actually this function of x1 x2. So if it is x3 dot, so the function will be f3 x1 x2 x3. So if the system is written in this structure, so we can say system is in recursive structure. So now, so here where f1 and f2 are the nonlinear function, let's assume it nonlinear function, and u be the control. This is the control input, you can say. Now our objective is design U in such a way that X1 tracks X1 desired. Okay. And the overall closed loop system is stabilized. So this is our mission objective for this problem. So here you'll be using backstepping based control concept, and we'll validate all the loops what you have considered here. This process will move on. Okay. So first step, we're gonna step one. So solution, step one. So here first we'll define the error, the tracking error for first subsystem. We can write, let us define the tracking error G1 equal to X1 minus X1D. So this is the error variable for the X1 subsystem. And the dynamics, we can write G1 dot equal to X1 dot minus X1D dot. In place of X1, we can write X2 plus F1 X1 minus X1D dot. Okay, so I have written the full equation, X1 dot equation. I have substituted in place of X1 dot. And let us define this equation number 1. Now step 2. Step 2, here let us define, here we're going to define the virtual control for X2. Okay, so let's assume, so this X2 will be the virtual control for G1 dynamics. So let us write consider X2 as a virtual control input, and design the stabilizing. So in this particular topic, you will have more than 5-6 examples, and I hope through these examples you'll have better understanding to design backstepping control for the nonlinear system. So design the stabilizing control law for G1. So for this, let us choose alpha 1 be the virtual control input for G1. So here this is how we are choosing, and this is X1D dot. So here this is K1 be the control gain parameter, which is positive control gain. If you notice carefully, if you substitute this function alpha 1 in our G1 dynamics in place of X2, then G1 dynamics will be stabilizing, asymptotically stable function. So we will prove this through the Lyapunov. So if you now, let us define, this is equation number 2. Okay. Now, combining equation 1 and equation 2, we can write G1 dot equal to minus K1 G1 plus X2 minus alpha 1. So if you notice here carefully, once these two parameters are equal, then this become a stabilizing function. This stable dynamics, right? Asymptotically stable dynamics when x2 minus equal to alpha 1. So this is what we have done, right? So in place of x2, we are choosing alpha 1 be the stabilizing function for G1 dynamics. So now step 3, we will prove this through Lyapunov. Step 3, let us define our Lyapunov function as V1 equal to 1 upon 2 G1 squared. So this is the dynamics equation we are having. And for this, we are choosing the Lyapunov function in the structure. Now from this, we can write V1 dot equal to G1 dot. And in place of G1 dot, we can substitute this expression. So minus Q1 G1 plus x2 minus alpha 1. So now if x2 equal to alpha 1, we can say this is basically virtual control, right? Alpha 1. So we can write v1 dot equal to minus k1 g1 square. This is less than equal to 0. So this is, we can say, negative semi-definite. And this is through this, we can say that system is stable. So how you are checking stable? So if you substitute, so for this condition, from this equation, we can write G1 dot equal to minus K1 G1. So we can write for x2 equal to alpha 1, we can write G1 dot equal to minus K1 G1. So this is basically globally asymptotically stable. So this definition we have done in our previous lecture, what is globally stable, asymptotically stable system. And here, why it is stable? Because here K1 always positive. K1 is positive here. Now we'll be designing the overall control U for the entire system. So now let me write one note to help to understand better how we can find the error for the Z dynamics, G2 dynamics. So to achieve this, this means this asymptotically stable system, we can write the state x2 must be equal to the virtual control alpha 1. But since x2 and alpha 1 start from different initial values, we must design the control force for x2t so that, or we can write here control force to track x2, or we can write further for x2 to track alpha 1 of t. So this is, so here in this case, we can write step 4, in this condition, let us define, define the error between x2 and alpha 1. So in this case, we can write g2 equal to x2 minus alpha 1. Or we can write g2 dot equal to x2 dot minus alpha 1 dot. Or we can write, in place of u2, we can write u plus f2 x1 x2 minus alpha 1 dot. So now we'll be designing the overall control U for the entire system. So here step 5. So now we have to design this U, control U to stabilize J2 dynamics. So now let us choose U as U equal to minus K2G2 plus, it should be minus F2 x1 x2 plus alpha 1 dot. So if you notice here, in place of U, if you substitute this expression, so we'll get Z2 dot equal to this part. So it is also stable dynamics. So because K2, so here we can write K2 is a greater than 0 positive control gain parameter. Now, let us define this equation number. Let us define, this is, for example, 3, and this is 4. Now substituting 4 in equation 3, we can write Z2 dot equal to minus K2 C2. So this is our stable dynamics. Now we'll prove the overall stability of the system. Step 6. So in this stability proof, we'll come up some condition for the control gain parameters, which will help us to choose the specific value of the control gains for practical examples. Now let us define the Lyapunov function for the entire system. V2 equal to V1 plus half G2 square. So here V1 we know half G1 square plus half G2 square, or we can write V2 dot, we can write G1 dot and plus G2 dot. In place of G1, we can write, in place of G1, we can write, just a moment, G1 dot, we can write minus K G1 and plus x2 minus alpha 1, right? And plus G2 dot we can write minus K2 G2. So this expression, in this expression, we can write this expression. In place of this, we can write also G2. So we can further write G1 minus K G1 plus G2 plus G2 minus K2 G2. And from this, we can further write minus K1, this should be K1. K1 G1 square plus G1 G2 minus K2 G2 squared. But we know that using the fact, we can write G1 G2 is always less than equal to half G1 squared plus half G2 squared. Now, if you substitute this value, this condition in the previous equation in P2 dot, we can write minus K1. We can write this expression less than equal to, since we are using in place of this, we are writing this expression, so it will be less than equal to. So we can write K1 G1 square plus half G1 square plus half G2 square minus K2 G2 square. And from this, we can write minus K1 minus half G1 square minus K2 minus half G2 square. So now if K1 is greater than half and K2 greater than half, P2 dot is less than equal to 0. So this ensures stability of the overall system. Now we have proved the overall backstepping process for this particular example. Now from the above analysis, we can come up the main control structure, which will be useful for designing the MATLAB code. So from the above analysis, the controls are U equal to minus K2 G2 minus F2 X1 X2 plus alpha 1 dot, and alpha equal to minus K1 G1 minus F1 X1 plus X1 D dot, and G1 equal to X1 minus X1 D, and G2 equal to G2 minus, this should be X2 minus alpha 1. So this is our controls for the system we are designing. Now we'll go to the MATLAB code and how we can validate the whole concept and verify the result. Okay. So here, whatever the process we have done in this lecture, it is there. So we have taken the as per the stability condition. This is the values we have considered, and in this case, K1, K2 chosen like this, and these are the initial condition for X1 and X2 not X1, X2, and this is the desired dynamics for X1, and the derivative of X1 desired is this, and total time span of simulation 20 seconds. And we have used OD45 to solve this problem. And these are the MATLAB code for figure. And here we have defined two variables, X1, X2, like that. And these are the nonlinear function we have introduced in this example, 0.1 X1 square. Here basically we have chosen F1 equal to 0.1 X1 square and F2 equal to 0.2 X1, X2. So these are the nonlinear function we have considered in this example. And we have, this is the error variable we have chosen, G1, this, and alpha, whatever we have taken from the analysis. This is wrote here. and G2 equal to x2 minus alpha 1. And this is the overall control which we have obtained here, this expression. And this is the derivative part of the x1, x2. So now if you notice here in the result, x1 tracks the desired, which is dotted line with red color, and x2 also stabilizing. So this is how we can design the backstepping based control for this nonlinear system. In the next lecture, we'll come up with the different examples and how we can solve also through MATLAB. Thank you.